Now remember this. Let's talk about black body radiation, or something that has an emissivity of 1. Now there's nothing that has that. You can approximate that, but you can't actually produce it. There's nothing in the universe that's known to have an emissivity of 1. It's a theory. But it's close enough that black body is defined as a body that absorbs all the radiation that falls on its surface. That is, nothing is reflected. Well, look at me. You can see me because some of the light that's hitting me, mostly the visible range, is reflecting off. It's coming from the light source, hitting me and reflecting off, and then you can see my image. That's what happens in regular photography. That's what happens with your eyes normally. If it didn't reflect the light, you couldn't see it. That's the problem when there isn't light. No light is making it from the object to you. That's the benefit of night vision goggles, because or thermography, because in night vision goggles, what little light is there is amplified, multiplied by the device itself through phosphorus, and that light makes an image that you can see. In infrared, you're actually seeing the radiation given off by the body, not the reflection of the body. But again, actual black bodies don't exist in nature. It's approximated by a hole in a box that's filled with highly absorptive material, so that a lot of the reflections that would normally get to you are absorbed at various angles. And so that's how you approximate a black body, getting very close to 1, but even that fails. This was fully described by Max Planck, the physicist, a long time ago, and in defining what a black body would be, or what it would be like, how it would behave. A black body is a hypothetical body, again, that completely absorbs all the wavelengths of the radiation incident to it. That is, that come into its body. It's all absorbed again. That's a black body. Remember, radiation is the electromagnetic emission that comes off of something at its surface. And if we double the temperature in Celsius, we get 16 times the radiation from that surface. If we triple the temperature, we see 81 times the amount of radiation. Now you start to see how a thermal imaging device can assign different colors to the different radiation coming off of let's say, a single wire or device. Why there is a gradient, why a wire will wick down to the hottest point. We saw earlier a wire that was wicking away from the contact point, an indicator of it's actually pointing to where the heat is coming from. In the image at the bottom right, tell me why I look hotter than the 99 degrees Celsius metal that's around me in the photo. To know that, you need to know that's stainless steel, so it has a relatively low emissivity. Some of the variations in the heat that you can see are due to the pattern that was scratched into its surface to give it a pattern. Some is due to the heat flows that are on the inside and the way the heat is flowing through the mass itself. So, but why do I look so much hotter? Well, there are, of course, two issues. The first being the low emissivity of the stainless steel device. And then conversely, its reflectivity, the very reason my image is reflected at all. Lastly, you have the additive effect, where my reflection, as you are seeing in that reflected area, you are seeing both that energy emitted by the device and the energy reflected as my heat pattern. And there's more reflected than there is emitted, even at that higher temperature. That's why we get a thermal reflection. That's why when you go into the field, you'll be taught, when you see a hot spot, to dodge back and forth, to change the incident of reflection, so that you can tell if that heat looks like it's moving, it's a reflected heat. Of course, if in this photograph I had moved to the left or right, the image would have moved with me because it was reflected. If somebody had, would have been very difficult, but if somebody had changed the device itself, it's funny because it's so large, but changed the position of the device itself, changed the angle the reflection wouldn't have been there, because it would have been reflected off in a different direction. Here I had to be perpendicular to that to have the reflection taken. Well, let's read part of that ISO standard, a cautionary note in this case. In most machine cases, it says, the lubricant will have the lowest temperature specification. The maximum allowable temperature should be stated as the temperature above which an unacceptable loss of component life will be experienced due to a loss of lubricant characteristics. Such reductions in characteristics may be immediate, that is viscosity, or long-term, additive depletion of the lubricant. Such criteria will tend to be design rather than material-based. This will require application to specific temperature criteria despite the possible use of common lubricants. Now remember, the ISO standards are very well thought out. Each is present for a reason. Let's examine the motor one more time in light of these standards. This is, again, the picture-in-picture of that one motor that we keep using because it's such a good illustration. The standard takes into consideration what is going to fail and why. In this case, the progression will be failure of the lubricant, then rapid failure of the bearings. It may be minutes, it may be seconds, it may be hours. It's according to how fast it's running, how much heat has been built up, which would be followed by the motor ceasing, machinery failure. But the electrical power continues until one of its components fails. But which one's going to fail? Will the breaker trip? Well, let's hope so. However, when a motor fails mechanically, it can actually experience materials failures. That is, the outer casing could break apart. Or other things can go wrong with it. Any kind of material failure. The materials that make up the motor itself can fail, breaking apart, sometimes explosively. And then you have flying metal in this space, potentially damaging people or other systems. Remember the last flight of the SST, where the flying part of the tire, which had failed, ripped through the wing, killed the hydraulics, caused the critical failure of the flight, and immediately all SSTs were permanently grounded. No more flights of the SST. In this case, very hot lubricating oil and sparks from electricity and potential fire could be the result of the equipment failure. This is why regular thermographic inspections are so critical to the life of machinery, to electric systems, and all those systems which are dependent on them. Lastly, what types of things can be understood better using infrared thermography? Well, nearly everything, from animals to cars, from desalination devices to electronics, from machines to electrical connections. You need to understand what you are looking at, how the heat got to the imaging device, and what that image means. You have to analyze that to see what is going on. From here, refer to the curriculum listing for the remainder of the classwork and the reading assignments and the reports and the testing requirements, and good luck. Remembering that luck tends strongly to follow those people who work hard.